commissioning of the $3.6 billion deepwater port of Chancay in Peru structurally realigns Trans-Pacific trade. By establishing a direct maritime corridor to Shanghai, the facility bypasses the Panama Canal and North American transshipment hubs. Transit times from Peru to China drop from 35 days to 23 days. This 12-day reduction compresses the maritime supply chain by over 34%. For Brazilian agricultural exporters in western states like Mato Grosso, routing cargo overland to Chancay cuts transit times to 28 days. This is down from 45 days via Atlantic ports. The operational economics are stark. Shipping lines save an estimated $375,000 per round-trip voyage for a single 18,000 TEU vessel. The primary constraint on South American Pacific trade has been physical harbor depth. Most regional ports cannot accommodate modern ultra-large container vessels, limiting cargo efficiency. Chancay features a natural draft of 17.8 meters. This makes it the only port on the South American Pacific coast capable of hosting vessels carrying 18,000 TEUs. In comparison, neighboring Callao is limited to 14,000 TEUs, while Guayaquil is restricted to 8,500. This deepwater capacity eliminates the need for regional feeder networks. It consolidates cargo handling from 3 stages down to a single direct loading operation. The infrastructure is designed to capture massive commodity flows from the South American interior. By 2030, total cargo throughput is projected to reach 26.8 million metric tons. This volume represents approximately 25% of the total containerized trade on the west coast of the continent. Brazilian agricultural exports, mainly soy and corn, will scale from 500,000 tons to 11.5 million tons by 2030. Peruvian copper and mineral exports will reach 9.8 million tons annually over the same period. This direct pipeline secures critical resource access for East Asian industrial supply chains. The global steel industry's transition to electric arc furnaces faces a fundamental metallurgical barrier. While total scrap demand is projected to rise 32.8% by 2030, the supply of high-purity prime scrap is virtually static. This inelasticity stems from manufacturing efficiency. As industrial factories optimize production and reduce metal waste, they generate less prompt scrap. The resulting structural deficit will reach 32 million metric tons annually by 2030. This forces steelmakers to find alternative iron feedstocks to avoid degrading steel quality. This supply-demand mismatch has triggered a severe pricing divergence in scrap markets. The premium for prime No. 1 busheling over obsolete heavy melting steel has more than doubled from its historical baseline. In 2024, this spread remains elevated at $160 per gross ton. This premium directly erodes the operating margins of electric arc furnace operators. High-purity scrap is no longer a simple recycled commodity. It is now a highly contested strategic asset, narrowing the cost advantage of low-emission steelmaking. Deficit is concentrated in regions aggressively decarbonizing their industrial bases. China's push to double its electric arc furnace share to 20% by 2030 will generate an 18 million ton prime scrap deficit. Europe faces a 12.2 million ton deficit, accelerated by carbon border taxes. To bypass this bottleneck, global steelmakers must build 46 million metric tons of new direct reduced iron capacity. Without this massive capital investment in virgin iron alternatives, global decarbonization targets for high-grade steel will remain unachievable. The expansion of commercial satellite constellations and deep space missions has exposed a critical vulnerability in the aerospace supply chain. Traveling wave tube amplifiers, or TWTA, are the primary bottleneck. Between 2018 and 2024, annual global demand for these high-frequency amplifiers grew at a compound rate of 17%. This surge far outstripped a rigid global manufacturing capacity capped at approximately 800 units per year. Concurrently, the qualified supplier base consolidated by 40%. Only 3 global entities, Thales Alenia Space, L3 Harris, and NEC, remain certified for high-reliability spaceflight. Consequently, average procurement lead times escalated from 11.5 months to 27 months. This supply deficit now directly dictates the launch schedules of critical defense and communication payloads. Aerospace industry cannot easily substitute these vacuum tube devices with solid-state power amplifiers. The laws of thermodynamics and electromagnetics dictate this reliance at high frequencies. At the Ka band of 30 GHz, TWTA deliver 150 watts of power compared to just 40 watts from gallium nitride solid-state alternatives. This represents a 275% increase in power output. Furthermore, solid-state efficiency degrades to just 12% in the high-frequency Q-band and V-band. TWTA maintain 48% efficiency at these frequencies. Low-efficiency solid-state systems generate massive waste heat. This requires heavy, complex active cooling loops that eliminate any weight savings over a TWTA assembly. Primary barrier to scaling production is the highly specialized, low-yield manufacturing process. Producing a single space-grade TWTA requires over 816 hours of active processing. Environmental testing and burn-in alone consume over 44% of this cycle time. This is necessary to prevent catastrophic electrical arcing in space vacuums. The chemical and physical tolerances are extreme. Cathode deposition has a first-pass yield of only 78%, as submicron variations in barium coatings cause premature failure. Additionally, helical winding of the slow-wave structure requires submicron precision. Micro-pitch deviations during this 120-hour step result in an 18% scrap rate, cementing the structural bottleneck. The revitalization of Western munitions manufacturing has exposed a critical bottleneck in basic chemical synthesis. High-purity hexamine, a dual-use precursor required for military-grade nitramine explosives, has reached absolute capacity limits. Between 2021 and 2024, defense-allocated hexamine demand surged by 279%, rising to 55 kilotons. This rapid expansion completely absorbed the available surplus capacity of Western chemical plants, which has remained stagnant at 350 to 360 kilotons annually. By late 2023, surplus capacity was entirely exhausted. Military procurement is now in direct, zero-sum competition with commercial industrial sectors for this fixed chemical feedstock. This supply chain friction manifests as severe physical bottlenecks at downstream ammunition plants. Procurement lead times for military-grade hexamine have ballooned from 6 weeks in 2020 to 32 weeks in 2024. Simultaneously, the price index for acetic anhydride, a critical dehydrating agent in the synthesis process, has more than doubled. Vulnerabilities are compounded by extreme market concentration. Just 3 Western chemical conglomerates now control 92% of the high-concentration nitric acid supply suitable for defense applications. Expanding artillery shell and missile production is fundamentally constrained by these centralized, single-point-of-failure chemical nodes. Utility-scale compressed air energy storage requires massive underground salt caverns for high-pressure gas containment. Creating these caverns demands a strict 10-to-1 volumetric ratio of fresh water to dissolved space. A single 500,000 cubic meter cavern consumes 5 million cubic meters of fresh water, even at a high continuous injection rate of 250 cubic meters per hour. The dissolution process requires 27.8 months of uninterrupted operation. This timeline is dictated by the thermodynamic limit of halite solubility. This physical law caps dissolution at 360 grams of salt per liter of water, establishing a hard floor on leaching velocity. The secondary rate-limiting step is the disposal of highly concentrated brine. Surface water discharge offers the highest throughput at 8,000 cubic meters per day, but carries a 36-month regulatory permitting delay. Deep well injection bypasses some surface environmental concerns, but is constrained by geological reservoir pressures. This pathway costs $450 per cubic meter of daily capacity. Mechanical evaporators reduce permitting times to 12 months. However, they require $1,200 per cubic meter of capacity due to extreme thermal energy demands. This operational friction creates a severe divergence between decarbonization targets and physical engineering realities. By 2030, the global compressed air energy storage pipeline is projected to reach 21 gigawatts, requiring 84 million cubic meters of cavern volume. Yet, water and brine disposal constraints cap feasible cavern volume at 25 million cubic meters. This leaves a 70.2% structural deficit. Consequently, over 14.7 gigawatts of announced storage projects face indefinite delays. The industry must rapidly commercialize alternative geological media to bypass this physical bottleneck. Advanced semiconductor fabrication is running directly into the physical limits of specialized chemical synthesis. Global demand for electronic-grade phosphine gas is projected to outpace effective manufacturing capacity by 2025. This structural deficit is driven by the rapid scaling of high-density 3D NAND flash memory and advanced logic nodes. By 2024, global capacity utilization reached an acute 97.8%. This leaves the semiconductor supply chain with zero operational buffer for unscheduled maintenance or precursor shortages. Supply chain for electronic-grade phosphine is highly consolidated and geographically vulnerable. Japan controls 42% of global 6N purity synthesis capacity, creating a centralized bottleneck for Asia-Pacific fabrication facilities. Building new synthesis plants requires extreme capital expenditure. A standard 500 metric ton facility costs $95 million in the United States and $110 million in Japan. These high costs stem from specialized containment, cryogenic distillation columns, and safety scrubbers. While China holds 18% of global capacity, its output remains heavily weighted toward lower purity industrial grades. The transition to next-generation transistor architectures exponentially escalates chemical consumption and purity requirements. Moving from legacy 28-nanometer logic to leading-edge 3-nanometer gate-all-around structures increases phosphine consumption per wafer by 416%. High-density 3D NAND, with over 232 layers, represents the most acute bottleneck. This architecture requires 14.1 grams of phosphine per wafer start, a 1,075% increase over legacy nodes. Furthermore, advanced nodes mandate subatmospheric delivery systems using nanoporous carbon adsorbents. This safety-critical delivery method reduces effective cylinder capacity by 35%, compounding global logistics constraints. The Scandinavian peninsula has historically remained logistically isolated from the Central European industrial heartland. Rail freight must currently choose between a circuitous 160-kilometer detour via the Great Belt Bridge or slow, weather-dependent train ferries. The 18-kilometer Fehmarnbelt fixed link structurally bypasses this bottleneck. By establishing a direct subsea corridor, the project reduces the rail distance between Hamburg and Copenhagen from 480 kilometers to 320 kilometers. Transit times across all major Scandinavian-German corridors will fall by 40 to 50%. The current 45-minute ferry loading process at the Puttgarden-Rodby crossing is replaced by a continuous 10-minute rail transit. Removing this physical barrier triggers an immediate modal shift in European freight logistics. Following the scheduled €28 billion project commissioning, rail freight volume is projected to expand from 6.8 million tons to 12.8 million tons by 2030. This represents an immediate 88.2% increase in rail capacity utilization. By 2032, the corridor will displace approximately 3,000 heavy goods vehicles per day from regional highways. This transition aligns directly with European Union mandates to shift 30% of long-haul road freight to rail by the end of the decade. It integrates the resource-rich Nordic industrial base directly into the continental supply chain. The economic viability of this corridor is driven by fundamental engineering upgrades. The new subsea tunnel permits maximum freight train lengths to scale from 650 meters to 835 meters. Daily freight capacity will expand by 300%, rising from 30 trains per day to 120 trains per day. Furthermore, reducing the maximum track gradient to 1.25% lowers energy consumption per ton-kilometer by up to 40%. Unlike legacy ferry routes, the subsea tunnel operates at 99.9% reliability, unaffected by Baltic winter weather. This physical intervention secures a highly predictable, high-capacity supply line for heavy industry. Maritime transport of liquid hydrogen requires mastering extreme cryogenic states. At minus 253 degrees Celsius, hydrogen must remain just 20 Kelvin above absolute zero. The thermodynamic properties of liquid hydrogen make it highly volatile. Its volumetric latent heat of vaporization is only 446 kilojoules per kilogram, compared to 510 for liquefied natural gas. This low threshold makes the cargo highly sensitive to parasitic heat ingress. To limit daily boil-off to 0.20%, carriers must bypass standard polyurethane insulation. Achieving this target requires either an unfeasible 800 millimeters of foam or advanced vacuum-insulated double-wall containment utilizing InVar 36 membranes. Transition to a global hydrogen trade is bottlenecked by specialized shipyard capacity. Projected demand for large-scale liquid hydrogen carriers reaches 110 vessels by 2035. However, global shipyard capacity can support fewer than 8 deliveries annually. This deficit is driven by extreme fabrication tolerances. Welding the INVAR 36 containment membranes requires specialized automatic tungsten inert gas systems. Fewer than 250 welders globally hold the required ISO 9606-4 certification. Furthermore, non-destructive testing failure rates must remain below 0.05%. Any microfissure risks hydrogen leakage, embrittlement, and catastrophic failure of the outer carbon steel hull. These physical and labor constraints double the capital cost of hydrogen transport vessels. A standard liquid hydrogen carrier is projected to cost $360 million, compared to $180 million for an equivalent natural gas vessel. The cargo containment system alone drives 40.2% of this total expenditure. This represents a massive premium over the 25% allocation seen in natural gas carriers. Costs are further inflated by specialized raw materials like polymeric MDI and high-purity silica. These chemical precursors face localized supply chain constraints. Additionally, safety systems add $20 million per vessel. Continuous nitrogen purging and subatmospheric vacuum pumps are mandatory to prevent explosive oxygen-hydrogen mixtures.